So, I mean, we don't need to do this because we've already done it. We don't really need to do this because we've kind of talked about that. When we talk about the computational methods that we'll talk in this class, we will exclusively talk about finite element methods. And we won't talk about smooth particle hydrodynamics, we won't talk about boundary element methods, distinct element methods, or lattice-Boltzmann methods, because time is going to be too short. They're all very interesting methods to use with very specific applications. But I think the emphasis of this class, or this short course, is to be able to present the material not in a mathematical way, but in a much more physically based approach. So that's always my intention in this class. To try and make the case why, when you use finite element models, the same code will execute one-dimensional, two-dimensional, three-dimensional, or nominally four-dimensional models. Four-dimensional would be time domain as well. And so that occurs in the same code, and there's a certain reason that finite element and other numerical models are able to do that. So we'll introduce that as we go through it. But the real crux, I think, of this activity we have going here is to talk about the coupling between models. And this interaction, we've made the case already that effective stresses driven by chemical changes, thermal changes, fluid pressure changes, and maybe loading changes in total stresses that are applied, have some influence on permeabilities and therefore on the response of reservoirs. And so that's really the emphasis of this class, is how do we couple those fields together to be able to figure out what the evolution of effective stresses are. And so our path through this is to be able to illuminate that more than anything else. And with respect principally to mechanical effects and due to heat, fluid transport, and dissolved mass. So this would be, in terms of THMC, we've talked about this acronym, thermal, hydromechanical, chemical behavior. This would be mechanical, this would be thermal, this would be hydraulic. It doesn't have to be water, which hydro suggests. It could be other liquids. And the mass dissolution would be chemical behavior and reaction. And so those are the kinds of things we'll talk about. And so it's easiest, I think, for me to demonstrate this just by reverting to a model. So bear with me, and I'll start this up. You don't have access to this, but it's instructive, I think, if it works in full screen mode like this, to be able to do it. Let me do this. COMSOL Multiphysics is a program that's floating around. Oh, that's, I guess that's a bit temperamental now because of the screen, but let's see if... doing some strange things. It's the first time I've had it open with the on the projector screen, so maybe it doesn't like this mode so much. Could be disastrous doing this. So it worked just fine 10 minutes ago without this geometry. Maybe. Don't use Macs I don't use PCs very much, but I guess this control panel, right, where you set the display characteristics. Let's see if that works. I don't want to do that. Just resolution, maybe it's that. Yeah. All right.
I think you need to maximize virtual machine first. By clicking the green button.
What green button where? On the previous screen?
The one which is...
Oh, the green button.
Yeah, the green button up there. Down there. Yeah, that there, green button.
Okay. Right. Then you think it'll do it now?
Maybe you just get out of that display adjustment and check out your console. back to your link. What was the thing that you chose? Medium or larger?
Yeah, it was on this. But it wanted to.
This make your font really small.
Doesn't actually.
Larger.
Yeah, it says. Or maybe it's done it already.
Could you just activate your console by clicking the icon down there? Next one. Yes.
Thinking it may just have hung. Yeah, but it takes even more time on this because it's actually not behaving very well. I think it's got a graphics card component that's missing. Let me exit out of that. Close the program. So this is the wonderful program that you could use to solve all of the problems that you want to solve. But we'll see how well it works for us. How do I get out of this? Is that? Let's try this here. That's a bit more promising. All right, so we're trying to make the case that finite element methods are the way of doing things. So this is a code that allows you to operate with multiple physical systems. And so we'll find out that the systems that we're solving are really partial differential equations. And partial differential equations can be zero-dimensional, dc dt. They can be order 1, dc dx in space dimension. Second order, d2c dx squared. And so individually, the components of the partial differential equations will have matrices that are specific to that PDE. And you can compile those to be able to solve the appropriate system equations that you want to deal with. And so we'll talk about fluid flow, but that's heat flow is an analogous problem to fluid flow. And so just get a feel for exactly what these kind of models allow us to do. And so I guess it may allow me, I could just maximize it in the screen, I suppose, might do it. It doesn't, it's cutting some off though. So let me instead try and get to the bottom if I can. No, I didn't want that. No, it'll be okay for now. So to be able to make models, you need to have a geometry that you deal with. You apply some interesting features to that geometry. Let's see if I can do it. It's good enough. It's not quite in the center. I think I can combine those and I can do the empty part. And so we could look at heat flow in a plate that has a insulated hole in it somewhere, insulated on the boundaries. And merely what we're going to do is we're going to solve the appropriate partial differential equation in this domain. We need to put boundary conditions on it, which we can do by applying appropriate boundary conditions. If I can get this out of the way and deal with this. And so I'm just going to set this up so it has a temperature defined on one side, which is 1 on the left side. A temperature defined on the right side, which is 0. And by default, this is an insulated boundary, this is an insulated boundary, and this is also an insulated boundary. And so if you're flowing from a high pressure or temperature on the left-hand side to a lower pressure or temperature on the right-hand side, then the flow will just occur and it'll go around this component because this is actually insulated or an impermeable boundary if you think of it in a fluid transport sense. And this hopefully will solve the system of equations, and it will come out giving a result, which if we plot, for instance, plot streamlines, because they're quite instructive, I think that'll do. Yeah, so you got to get the picture. So very, very, very simple. So it's a simple model. It's looking at heat flow or fluid flow from this side. This is the individual trajectories the transport of heat would follow, or fluid flow if it's fluid flow. This is insulated, so it goes around that. And it's a relatively straightforward process. What we are going to attempt to do is not just solve for, say, one form of heat flow, but what we might like to do is be able to solve for another simultaneous system. So what we could do is we could add another heat flow problem on top of this, and another, and another. And if we went back to actually run these models, what it would do is it would solve all of these heat flow models for this geometry and do it independently of the other models. And so here we've potentially put in 3 models. I guess I could delete one, I guess, remove one. So here we have 2 models. We could also set this up as well, I guess. If we did this, see if it'll let me do it. Might be a bit temperamental, or it might be slow, or it might not work at all. Maybe it's going to work, maybe not. It looked like it wanted to work for a moment there. But what we could do is we could solve both of those models at the same time. But what they don't have in them, they don't have any innate coupling between them. And so our approach to being able to look at these systems, and I think I'll probably have to close this now, is to be able to understand if we're looking at thermo, hydro, mechanical, chemical responses, what we could do is we could look at the hydro part, the flow part, and understand how to put the system equations together to be able to look at that. Understand that well enough in itself. We could look at the chemical part to be able to understand how mass is transported in the system. They're actually very similar equations, as are the heat flow equations. And once we know how to do that, we have the ability to solve those 3 systems independently of each other. Once we have that, if we know what the linking between those individual systems are, then we can link them in an appropriate way so that they're physically linked in a mechanistically consistent way, and we have our overall solution. So that's kind of the approach that we'll take. It hasn't like this, so let's close the program, so let's not worry about that. But that's a useful way of thinking about it. So what it's done is it's taken this geometry with a hole cut in it, it's filled the whole geometry up with triangles which have completely filled the domain, and on these triangles it has tried to solve things in terms of the nodal parameters that are the vertices of these individual elements. And so what we need to do is find out how to be able to put those things together. So that's our next task in all of this. I want to get out of this. I don't know. Do I know how to get out of the virtual machine? How do I unminimize it? We'll do this if it. That's the problem with maximizing it. Is it's responding. I'm going to do this. I'm going to kill it. I'll run it in the background, and that'll be good enough for us. So that's our approach to this. Excellent. We're in business. And so our ability to do this is really to be able to understand individually. We'll talk about fluid flow first. Then I think we'll talk about mass transport. Thermal behavior is the same as mass transport. They're all the same system equations. And then we'll talk about mechanical behavior, which is slightly different. And then we can start thinking about combining them. So that's where we go. So that's our 15-minute introduction. History of FEM. Well, it's a method that came out in the mid to late 1950s. A couple of groups were both working on it. A group out of Berkeley, which is Ray Clough, who was working at Boeing at the time. The Cold War was on. The ballistic missiles and jet fighters, being able to design them without physically building models, but being able to do numerical models was in its infancy, and this was what finite element methods were developed to do, because different from previous numerical methods, which were now feasible because of digital computers, which are coming into their own around that time, they could deal with much more irregular shaped bodies. So you saw that we just had a system with a hole cut in it. If you wanted to have a rectilinear square grid to approximate that, you'd have a hard time representing the hole because it would be a jagged little spike. So finite element methods, because they had irregular elements, had some advantages of the existing finite difference methods. So there are two groups working on it. Clough, who is working at Boeing and Berkeley. Argyris, who is German, working at RW Ruhr-Westphalia Technische Hochschule in Aachen in Germany. Both came up with the method at the same time. And since the 1950s, is when it was developed primarily for solid mechanics. It's been developed and used for fluid flow, transport, heat flow, and all manner of things. So that's kind of its origins. And so it's a relatively mature discipline right now. And so what we'll talk about is we'll skip over to not worry about the rest of those individual components, but we'll skip to talk about physically how we might solve these systems. There is a paper in here by Felipa, which some of you might be interested to look in. It talks about the history of FEM and how it evolved, which is quite nicely written. But I think we'll probably get more into the nitty-gritty of what's going on rather than dwell on that. It's quite nicely written, this paper.